So let's consider what we were doing last class meeting when we were summing up those areas. We were actually going through and manually, we figured out the width, figured out the height, and we were multiplying each one together. And that's a very, very tedious process. But what we were actually doing is we were summing up, if I put this in summation notation, we were summing up the areas from I equals 1 to n of f of c sub I times delta x sub I. Alright, and so this f of c sub I, this is where we were getting the height of each rectangle. And then this delta x sub I, it was the same every time. It was the same width each time. Okay? And then we worked that out, and whenever we worked that out, we added all of our answers together, and we got some answer, some number. We're going to call that number L. Well, what if I actually let this delta x, remember delta x is like the change in x? It is the change in x. What if I let the delta x actually approach, or the delta, the change, approach 0? So to do that, I would take the limit as the magnitude, or the length of delta, approaches 0. These double lines here, that means magnitude or length. Not a very hard concept. Just, we're actually thinking about lengths here, something we could take a ruler and measure out. What if I let that change approach 0? So that means each width is approaching 0, so I'm getting an infinite number of rectangles under my curve. Okay? So if this limit actually exists, then the function f is said to be integrable, or you can integrate it, on some interval from a to b. So if this limit exists, f is said to be integrable on some interval, some closed interval from a to b. And the limit as delta, or the change, approaches 0 of the sum I equals 1 to n of f of c sub I times delta x sub I. And don't let all of this notation confuse you. This is a limit notation. This is summing up something. This here, this is the height of those rectangles. Right there, that's the height. And then this here, this is the width of those rectangles. So if I can actually figure out some value when I work out by hand, I know I can't work out an infinite number of rectangles, but if I use my rules for limits, and I'm able to actually get out an answer here, all of this is actually equal to the integral, that's the integral symbol, from a to b of our function f of x dx. Alright, so if this limit exists, if I can actually add up an infinite number of those rectangles and get a number, then that's equal to the definite integral. That's what that's called, the definite integral. you learned about the antiderivative and the integral earlier, and we didn't have any numbers that we put here. These will be numbers until we get into multivariable calculus. These are just regular old constants usually. And so that's the only big difference, is that you have numbers here instead of just a regular integral sign. Now, if you have just the integral sign, that's a definite integral. So how is the indefinite integral different from the definite integral? And I may have just misspoken. The indefinite integral would be one where you don't have these boundaries or these limits. And the indefinite integral is one where you, well, that's the one where you don't. The definite integral, you have numbers. The biggest difference there, as far as students are concerned, the mistakes that they make, would be that you sometimes with a definite integral like this, they put plus c with their answer. And you don't have to do that with a definite integral, because you actually get out a number answer at the very end. So that's the biggest difference. You have to remember, if you don't have the boundaries, then it is an indefinite integral to put plus c, but with definite integrals we don't, because we're going to actually get a number answer out at the very end. Okay? So this, whatever number this is here, this a, that is our lower limit of integration. And then this top number here, b, that is our upper limit of integration. So what does that mean? That means that the a here, this always needs to be the smallest number, and the b here needs to be the largest number. Okay, so if you ever set up an integral and you have it backwards, that's just going to give you the opposite answer. If you're to swap a and b here, you get the negative answer out. Okay, so let's see how we can actually, how we would work out one of these definite integrals. So let's say I had the integral from 0 to 5 of 2x dx. And so what this means is, this is a definite integral. You can see my interval is 0 to 5. My lower limit of integration is 0. My upper limit of integration is 5. And so what I want to do is I want to integrate this stuff in here. So integrate the 2x. So you add 1 to the power, divide by the new power, and you get x squared. Now usually if this was an indefinite integral, you would put plus c. But since this is a definite integral, what you want to do to denote that you have to do some more work, make a little bracket here and just say from 0 to 5. I'm just copying over the limits again here, and that reminds me that I need to evaluate these now in my answer. And so the way you do that, you plug in the upper limit of integration, plug in the 5 here, and so you'll have 5 squared, and then you always say minus, and then you plug in the bottom limit here, and that'll be 0 squared. Alright, so my answer is 5 squared would give me 25, minus 0 squared, of course, is 0. So my answer is 25. Now, I want you to, real quick, I'm going to give you about a minute, I want you to sketch, what does this actually show us? How could we represent this graphically? So if I sketch f of x equals 2x, alright, so whenever I plug in a 0 for my x, I have a 0 for my y. Whenever I plug in a 1 for my x, I have a 2 for my y. When I plug in a 2, I have 4. When I plug in 3, I get 6. When I plug in 4, I get 8. And when I plug in 5, I get 10. Okay. And I'm just going to stop my line there because I'm only interested in the values between x equals 0 and x equals 5. Right? And so what does this actually show by working out this definite integral? That's going to give me this area here under the curve to the x-axis from x equals 0 to x equals 5. Okay. So kind of looks like that makes a triangle, doesn't it? Well, if that's a triangle, then I could actually just use algebra to work this out. Let's see if that works. Let's see if algebra, or if you know, the geometry that I learned at a very, very early age, you know, 3rd, 4th, 5th grade, would work on a triangle like this. The area of a triangle is what? 1/2 base times height. So 1/2 times, what's the base here? How many units? 5 times the height, 10. So that's 1/2 times 50, or 25. So yeah, this calculus stuff actually works, right? It gave us the area under this curve between 0, x equals 0, and x equals 5. You may say, well, why don't we just always use this? Well, we're not always just going to have a, we can't always just use these geometry formulas because we're not always just going to have straight lines. Just in this case, what we figured out could have been solved using really, really elementary math, right? Okay, so let's see what happens. What if I took this same function, and I'm going to extend it here, extend it down, and what if I integrated, say, from -4, let's see, there's -4, to 5. So I wonder what happens then. Because you see, if I extend this line here, and when you integrate, it gives you the area beneath or above the curve if it's actually under the x-axis to the x-axis. So if I just did the integral, how about we start out and let's just do the integral from -4 to 0. This black triangle that I have up here, I know most of you could figure out the area right now. You could just say 1/2 base times height and figure it out. But let's see what happens if I take the integral, say, same integral, from -4, x equals -4, to x equals 0. And so if I do that, then what happens? If I plug in a 0 here, I get 0, minus, if I plug in a -4, I get what? 16, so 0 minus 16, that's -16. So what would be the problem with that answer? I can't have a negative area. However, the way that this works, all of this works, this is the correct answer. -16 is the correct answer. So if this was an application problem where maybe I was trying to figure out an area so that I could cut out the right material, I would want to make the area a +16. But as far as just the integral here, just the integral itself is equal to -16. So you would just have to be able to make that adjustment if this was an application problem. So you could really say that this definite integral does not represent the area of the region, not as the answer is given here. Now you'll never, as far as just working out integrals in here, you don't have to worry about changing them from negative to positive. We just take the answer as it is, unless I tell you otherwise. So, you know, definite integrals can be positive. Definite integrals can be negative. Definite integrals could even be 0. So, well, how does an area equal 0? It's that maybe area on one side of the positive area and the negative area ended up canceling. It's not really a negative area, but the negative values end up canceling out and you get 0. So that's okay. So I did tell you I wanted to integrate from -4 to 5, and let's see what happens then. So if I do that same integral from -4 to 5, then let's see what that would be. That's x squared evaluated from -4 to 5. So that's 5 squared minus -4 squared, or 25 minus 16, which is equal to 9. And so would 9 give us the actual area of these two regions? No, it wouldn't. It's worked out correct. That's the way that definite integrals work. I guess you could say that would be one drawback if you're just worried about area. But look what that actually gave us. That actually gave us the area that we started with, 25, and then minus 16. So the integral from -4 to +5 was actually the same thing as the integral from -4 to 0 plus the integral from 0 to 5. Okay, so that's just the way that it works. All right, let's see a few other integrals real quick and see if we can translate those over to what they would look like if we were to graph them. Maybe we can get a couple of shapes that we're familiar with. All right, let's first look at this integral. The integral from 1 to 3 of 4 dx. So if I just do the number crunching and I don't worry about what I'm actually figuring out or something, how this could be applied maybe to the graph, then I would just say, okay, the integral of 4 is 4x, and then I'm going to evaluate that from 1 to 3. So now you plug the 3 in, so that's 4 times 3, minus, plug the 1 in, 4 times 1. So it's going to be 12 minus 4, or 8. And so what would that actually, how could we apply that, maybe say to the real world? And there's a million different applications, but if we were just to look at the graph, if we let f of x equal 4, okay, so hopefully you can draw a graph a little bit better than I did here, but if I let f of x equal 4, that's just the horizontal line that goes through 4. Now, look at the boundaries, x equals 1 to x equals 3. So what am I actually finding? This is x equals 1 here. This is x equals 3 here. So I'm actually finding the area under the curve, or the area of this shape right here. And that's a rectangle, right? So if I was just to come down here and and look at this, I could say, okay, that's 2 units, that's 4 units. So 2 times 4 is 8, and that is the answer that we got there. Okay. let's look at this. The integral of x plus 2 dx from 0 to 3. I'll give you a second to do that. So that will be 2x, I'm sorry, that would be x squared over 2 plus 2x evaluated from 0 to 3. Alright, so that is 3 squared over 2 plus 2 times 3. So that's what I get if I plug in 3. Then I have to say minus, and since I'm plugging this into more than one value, you probably, just to get in the habit of doing, even though I'm going to get 0 here, probably want to put that in parentheses. Because if this wasn't a 0 and I actually got out numbers here that I had to deal with, then I would need to make sure that I subtract whatever I put in here. So plugging a 0 in here does give me 0, and plugging a 0 in here does give me 0. But again, get in the habit of putting whatever you plug in parentheses so that you won't mess up your math. Alright, so that's going to give me 9 over 2 plus 6, or 9 over 2 plus 12 over 2, which is 21 over 2. Okay. Let's see if we can sketch that real quick and see what type of figure that would give us. See if we're actually finding some area. Alright, so alright, so I have a slope of 1. This is f of x equals x plus 2. Slope of 1 and a y-intercept of 2. Alright, so at 0 I have 2, 1 I have 3, 2 I'm at 4, 3 I'm at 5. Okay, and that was my interval, 0 to 3, so that's where I'm going to stop. Okay. Let's add a little color to our life. Alright, so what type of shape is that? The trapezoid, right? Using geometry, you can figure out the area of a trapezoid by saying 1/2 times the height times base 1 plus base 2. And if you do that, 1/2 times the height is what? See, this height is what? 2. This height is what? 5. Well, probably want to think about the trapezoid like this is the top here and this is the bottom. That way the height stays the same here. So the height here would be 3, and then the length of this side is this side is 2, and the length of this side is 5. 2 plus 5. Alright. So that's 3/2 times 10. No, 3/2 times 7, which is 21 over 2. Alright, so what we figured out by doing that definite integral is actually the area of this trapezoid. Alright, on this next integral I'm going to show you how understanding the geometry would actually give you the opportunity to work out this problem without having to know how to do the integration, because we haven't went over how to integrate something like this. So the integral from -2 to 2 of the square root of 4 minus x squared dx. So this integral is actually a little more complicated than you would think. Just by looking at it, you may say, well, hey, I could just probably, you know, follow the same rules, but there's a big problem here. And if you think you can integrate it, try to integrate it on your own time. You know, try to integrate it and then take the derivative of your answer and see if you get this. This integral is actually an integral that lots of students have trouble with. It's requires a long formula that we go over maybe near the end of the semester. So again, the function looks pretty easy to deal with, but the actual integral is tough. Well, let's see if we just say, well, what is this the same thing as? Well, it's f of x, or y, equals the square root of 4 minus x squared. That's the function that we're dealing with. Well, what if I was to square both sides of this equation? Then I would have y squared equals, when you square a square root, that cancels out. So I'd have 4 minus x squared. And then if I move this over, I would have x squared plus y squared equals 4. And what is this the equation of? It's a circle, right? So what is the square root? What does that do? That makes it where I just have positive y, or positive values above the x-axis, because I'm only going to have positive y's to go with this graph. So this function here, this is actually a semicircle. Okay, just real quick, I'm going to sketch this circle, and then remember I only have positive y's because of this square root. No matter what you put under here, we can't have negative values, because you can't take the square root of a negative value and get a real number. So, but if I just wanted to sketch this circle, the center of this circle is 0, 0. The radius of this circle is 2. Alright, so 0, 0 with a radius of 2. It means you just go out 2 units in each direction. So we know the circle, if it was a circle, would intersect in those points. Since it's a semicircle, we're just talking about this right here. And so what we're actually trying to figure out with this definite integral is the area of this region. Or that's one way that we can interpret this definite integral. So I don't have the calculus skills necessary to work this problem, but I do have the geometry skills that I would need. We know that the area of a circle is what? Pi r squared. So the area of a semicircle here would be pi r squared divided by 2, or 1/2 pi r squared. What is the radius of this circle? 2. Alright, so that's going to be pi times 2 squared over 2, or 4 pi divided by 2, which is 2 pi. Okay. So imagine the type of integral that I would have to have so that whenever I plugged in a -2 and a +2, that I would get out some type of pi answer. What would I mean? So there is some crazy things, or some pretty advanced things that have to go on to do that integral, so that when I plugged in the numbers -2 and 2, I'd actually get out a 2 pi. Okay, I wouldn't expect you to have to figure this out on your own, but if you see one like this now, whether on a test or a homework or something like that, hopefully you'll be able to work that out. Now, like I told you earlier, definite integrals don't have to be represented by area. Okay, you can just find a definite integral just off of integrating and plugging in numbers. But it makes a little more sense if you can kind of relate it back to something that we learned at an early age, and you can kind of see how things work and why they work. Two special definite integrals. You probably won't see this, but if you have an integral from and to the same number, like for example, if I said the integral of, and it doesn't matter what I put down here, how about I put sine squared x cosine x tangent cubed x, this would be a pretty tough integral probably. But if I just have the same number here and the same number here, then if your boundaries are the same, that's always going to give you, and I'm bad because I didn't put dx, but if your boundaries are the same, that's just going to give you 0. So you have to have different upper and lower limits. If they're the same, it doesn't matter what you're integrating, you're always going to get 0. I told you that this was the lower limit, this was the upper limit. The thing that you're integrating is called the integrand. So if I ever say the word integrand, that's what I'm talking about, whatever you're integrating. Another property, and I believe I touched on this earlier, is that if you integrate something from A to B, if you were to switch these, you get the opposite answer. So if you go from B to A, then you're going to get the opposite answer. And notice whenever you talk, when you say this math, you always say the bottom to the top. So this is the integral from A to B, this is the integral from B to A. May or may not ever see any of that, but just in case you do. Alright, so let's look at one more example real quick of a definite integral. What if I have the definite integral from 2 to 4 of negative x squared plus 4x minus 5. Okay, so we need to integrate each term separately. Integrate each term. So that would be negative x cubed over 3 plus, it's going to be 2x squared over 2, or just x squared, right, because the 2 in the denominator would cancel that out, minus 5x. And then we're going to evaluate this from 2 to 4. Alright, so first I want to plug in the 4. So it's going to be negative 4 cubed over 3 plus 4 squared minus 5 times 4. Now what I would suggest doing, since you have a lot of terms here, is putting all of that either in parentheses or in brackets to kind of separate it. That's what we get when we plug in the top boundary or the upper boundary. And then you say minus, and now let's plug in the 2. So we'll have negative 2 cubed over 3 plus 2 squared minus 5 times 2. It's very easy to forget to put these parentheses and then just change the sign of one number and get the wrong answer. So make sure you don't do that. Make sure you plug in the top, kind of group all that together, and then this minus needs to be here. Minus, plug in the bottom, and group all that together. So this is going to be negative 4 cubed is 64 over 3 plus 16 minus 20 minus negative 8 over 3 plus 4 minus 10. Alright, so it's negative 64 over 3. Put those two together, you get a negative 4. So that's going to be minus 12 over 3. Alright, put these two together, you get a negative 6. So that's negative 8 over 3. That's going to be negative 18 over 3. So that's going to be negative 76 over 3 minus negative 26 over 3. So it's going to be negative 50 over 3. You may be tempted to get a decimal for this. Always leave things exact when you can. If at all possible, leave things exact.